So let me go back to this example where I properly label the objects. So everything is labeled by its composition series and shifted modules. And what I mean here when I shade this region red for P of phi 1 is that each of these objects has phase phi 1. Okay, so each of these objects is semi-stable at phase phi 1. The blue object semi-stable at phase phi 2, and the green object semi-stable at phase phi 3. And so, for example, the hard and narrow symmetry rotation of the projected injected 1, 2, 3, 4 is given by this. So with this is biggest phase, next biggest phase, smallest phase. So with the other slicing, which didn't come from the stability condition, the same kind of idea here, just as a note. For example, here's the composition series projected injected 1, 2, 3, 4. Well, this is not a hard and narrow symmetry rotation of 1, 2, 3, 4. I have to refine it a little bit. So the hard and narrow symmetry rotation is here. So these symbols here, 3, 2, 1, are occurring in a long order. And so the technology, the hard and narrow symmetry technology, collects them together over here to get a filtration which has the right sort of descending, strictly descending sequence. So I just wanted to address that. The second question I received in the chat, which Ana Garcia kindly forwarded to me, was whether or not the fact that the slices of slicing was a property of, that I'm imposing on the slicing or a consequence of the definition. So in the case when we have a stability condition, it's a consequence of the definition. Okay, so this is not something which is imposed. This is something which follows from the definition. I might say, I'll probably write up in the lecture notes a quick argument why that is the case, and I might say something about it later on today, but I may not, it depends on timing. So I want to recall last time, so I'm now going to go back to the blackboard. So I'm going to unplug this and hopefully that just turns that off. So I want to recall that star B is the set of locally finite this is so in the lecture notes I sent to the organizers, I gave them a quick sketch of how to define a topology on this space. This topology is not going to, well, it's not really going to be important for most of these lectures, so I'm just going to refer to those notes if you're interested on the topology. But essentially, what Bridgeland shows is what he calls a charge map. Which takes, so remember, stability condition is a homomorphism, which is a stability function, together with a pattern of slicing, the map which takes this perm down to the stability function, the center of charge, is a local homomorphism. And so the key theorem is that space of stability conditions is a topological manifold. very nice geometric space. This is the theorem of Bridgeland, and the general conjecture is, which I wish to address in this talk, is why we believe, to the best of my knowledge, there are no counterexamples. If the stability manifold is non-empty, then it is contractible. And then the point is, in physics, if this is true, then the geometric simplicity of this space makes various physical calculations much easier. So this is a very attractive thing for the physicists to have. So now I want to start thinking about this question. So I want to move from stability conditions to T-structures. So thinking about the connection between stability conditions and T-structures. So let me recall what a T-structure is. So a T-structure. Yeah.
Is there a simple example of stability condition?
Yeah. So if I, for example, take the perfect derived category of the dual numbers, this has no binding T-structure, so it has no stability conditions. That's the basic first example. And then generally, if you take any perfect derived category of something which is singular, this probably is going to happen. And also you've got the problem, so this is not, I mean, somehow this is bad news for cluster theory. Anything which is positive Calabi-Yau, so this probably, it depends on the size of the category, but most of the classical cluster categories which are positive Calabi-Yau, the Calabi-Yau symmetry stops in the cluster cases from having T-structures, so this gives you other categories which don't have this. In general, negative Calabi-Yau categories don't have T-structures. Something most positive Calabi-Yau categories are the ones with Calabi-Yau three-folds, they do. And so the second for this is you need Calabi-Yau three-folds in mirror symmetry. So a T-structure XY T is of subcategories. All my subcategories are full, such that three properties hold. First, X is closed on the shift, which can be formulated in the equivalent with the other conditions. It's equivalent to the Y path being closed under the inverse shift. There are no morphisms object in X to an object in Y. And everything in D can be built from X and Y using this star model we discussed last time, which is we call this is the set of D. So it's a triangle. So really, what is a T-structure? It's a torsion theory on a triangulated category. The nice thing about it is there's a distinguished subcategory. X intersect the shift of Y, which is called the heart. And this is the B. So a T-structure gives you a technique for obtaining an abelian category from a triangulated category. So you're essentially looking at, this is one method of looking at the abelian category sitting inside a triangulated category. And the nice thing is, so T stands for truncation, so these X and Y here are truncations. And if I do an X truncation followed by a sigma Y truncation or the other way around, then I land in the heart. This defines a homological functor. So T-structures give ways of getting homological functors on the category. So they somehow give intrinsic homology. So this is kind of the point of T structures. And then I want to restrict not to all T structures, but just a subset of them, especially one bounded. And the T structure is called bounded if the category is equal to the union of all the shifts of the X part and the union of all the shifts of the Y part. Okay, so morally what this says is that, so the T structure gives you a homological function, and being bounded says that D is behaving as if it's the bounded derived category of the half. It isn't the bounded derived category of the half, but it's behaving as if it was. So I'm going to state a lemma now, which relates a T structure with the kind of filtrations we saw in the last lecture, the hard and narrow sum filtrations. So if I have an abelian subcategory of D, this is the half. Of bounded T structure. If and only if two conditions hold. There are no homomorphisms from positive shifts of objects in H to objects in H. So this is like you see in the definition of the slicing. There's no morphism from an object of higher phase to an object of lower phase. And the second is for each non-zero object D in D, there exists a power. Like this. With each object HI in H and I1 bigger than I2 IS. So you get a strictly decreasing a filtration by objects in the heart, which is strictly decreasing in phase. Okay. So you see this is also exactly what you see in the definition of the slice. And because this is in a talk in a workshop on clusters, so we often write 2 as D equals the union of an I bigger than or equal to J sigma I H star sigma I minus 1 H sigma J plus 1 H J H, which you may have seen similar kind of formulas in cluster tilting theory. And I would sometimes even be a bit more lazy and write this as sigma H H H, where I'm assuming that any one of these is in, any object has a finite, sits in some finite particles. So the nice thing about this picture is you can kind of see what's happening here. So here is x. Here is y, and if I shift y, that's the intersection, which is the heart. So this is kind of a schematic of what a T structure looks like. With the cluster tilting setting, the silting setting, as we'll later see, the shifts are going in the opposite direction. This is the link between T structures, stability conditions, which is projection. Stability conditions on D and boundary T structures. Together with stability function. Okay. So in practice, in most representation theoretic context, one thinks about stability conditions in this language. So we think about specifying the heart and the stability function. And if you remember from the last lecture, specifying the stability function, I'm completely free to specify a stability function on a length heart. So if this is, if the heart is a finite length abelian category, then I just have to choose what the stability function does, the simples and the HN property I get for free. So when the heart is finite length, there's essentially no restriction here. It's give yourself, specify the heart and specify a function. So let me give a quick indication of the proof. So starting with the stability condition, say sigma equals ZP, so stability central charge plus slicing, and define X to be the extension closure of all the objects which have phase bigger than 0, Y the extension closure of all the objects which have phase less than or equal to 0. Heart is all the objects which, the extension closure of all the objects which have phase between 0 and 1, excluding 0, including 1. And then the slicing, so Z is stability function. The slicing the chain. That's how you pass from stability condition to a T structure with a heart with a stability function satisfying the HN property. Backwards, we have a boundary T structure. Z stability function on it. Set phi equals the semi-stable object or slope. Oh, sorry, phase phi or rule. What I do is I take the abelian stability condition and I just use the shift functor to extend this to the triangulated category. That's all I do. That's the bijection between stability conditions and halves with stability conditions. So one more definition. So I'm going to say x, y is algebraic if h has finite length with finitely simple objects. Simple. And I'm going to define CH to be the set of stability conditions in V having part H. So here in this, so a stability condition is ZP, and what this means, this bijection means is I can replace it by ZH, and CH is the set of all stability conditions where I'm fixing H. So I just vary the stability function of the central charge. And H algebraic implies CH is morphic to the upper half plane to the number of symbols. Because specifying a stability function just involves saying where I'm sending the symbols. So when I have an algebraic part, the chamber associated to it is very simple. So I want to talk about moving around the stability condition, space of stability conditions, the stability manifold. And so it's going to split up into a Wallman chamber structure, and these are going to be the chambers. So let me tell you how to change chambers. This is due to many people. So I'm just going to credit it to Happelrath, Marlow, probably Felicia and Triton. Pauksztello. Wolf. The first idea goes back to Happelrath and Marlow, and other people have come along and refined it, and I probably missed someone off the list. But so there's a bijection. T structures X prime, Y prime with, that's right, the X part sitting between the X part of the new T structures sitting between, so I should say, given X, Y, there's a bijection between T structures which sit between X and its negative shift. torsion pairs in the heart of xy. This bijection goes by, so I send a torsion pair EF to x prime, y prime, given by x star minus 1 t given minus 1 f minus 1 y. I'm going the other way. I got this right. Goes like this. Let me just give some notation and then I say, so I can never remember this, so let me tell you how to remember. So this here is called the right tilt. XY at EF. And I would typically write it as RTH. So I'm going to, by abuse, identify the T structure with its heart, and in a right tilt, I'm going to keep track of the torsion part of the torsion. Okay. So how do you actually remember this formula? So remember D is equal to sigma H star H sigma minus 1 H. Maybe I need a bit more, sigma minus 2 H. But actually I can refine this a little bit. Because it's a torsion pair. It splits into E star F then remember this is X and this is Y, and all I'm doing is moving. They can't see the red. How about blue? Or is this equally bad? So I just move 1/2 of the torsion pair to the right. So this is how I remember the formula. So a little bit of notation. If T is the extension closure some set of simples, we say RTH is admissible. That's admissible right tilt. If the torsion class has a special form, it's an extension closure of simples. So the point of this is that you're going to have to forgive some of my drawing here. I'm not very good at drawing in more than 2 dimensions. But so I'm going to sort of do a projection onto 2 dimensions. Right. So up here I have Z. I'm going to have Z of another symbol, Z of another symbol, and so on. Right? Really, I should be writing a different plane, different upper half plane for each symbol. Right. Right. I don't really need the 6 dimensions for this guy. So probably I can go S1 and S2. But the point is that if I move a symbol across the positive real axis, this corresponds to doing an admissible right tilt at the torsion curve generated by that one symbol. So remember my so where am I? Maybe I probably just erased it. Here's copied on. My stability conditions are there's the heart and the stability function. And I have a topology on this space. So I've got the notion of continuity. And this is the chamber is locally homeomorphic to these things, right? So I've got a fixed heart, and so I can move in a continuous way these charges, and this corresponds to moving my stability condition. So it's a continuous pattern of stability manifold. If I could do a continuous pattern of stability manifold, there's a few caveats because I'm not allowed various things to become 0. That causes a problem. If I move Z of some symbol so that it crosses this boundary, this corresponds to doing an admissible tilt that corresponds to admissible tilt. Right. Question by S1. If I do something similar on this side, I get an admissible left tilt at the torsion free class generated by whatever symbol I'm looking for. So the point is that stab D as chambers corresponding to hearts. Roughly, I'm looking at an algebraic class here, and walls, 4-dimension 1 boundaries. Corresponding to symbol tilts or irreducible. So the key take-home message here is that moving around the stability manifold corresponds to something we know very well in representation theory, is tilting theory. And this is how Silting theory comes into the story. What do I do on time? Do I take 10 more minutes?
5 minutes.
5. So, okay, so I try to explain a little bit of Silting. Right. point of this is that tilting of t-structures is actually fairly difficult to control. So I'm going to pass the Silting theory, because this has a mutation theory which reflects the mutation theory, the tilting theory here, but is easier to control. So I'm going to pass the Silting theory to understand this tilting theory, which is about moving around the stability line. So let me tell you what a silting object is. I'm going to think in terms of silting subcategories. So a subcategory M of D is pre-silting if there are no morphisms from any object of M to the shift of any object, positive shift of any object of M. And it's called pre-tilting if I shouldn't use just to say what tilting is. For any non-zero shift. Silting is just a tweak to the definition of tilting. If D is equal to thick M, so the smallest triangulated subcategory containing M, which is closed under direct summands, then M is. So the way to think about this is the pre-silting condition is that this says that the objects of M are linearly independent, and this condition says that it's bound. And if M is an object, indeed, say M is pre-silting if the subcategory generated by it, so the additive subcategory generated by it, so the advantage of talking about subcategories rather than objects is simply I don't have to talk about objects of two equivalents. I just take an additive generator. So let me show a quick example of a couple of silting subcategories, and then probably it's a good time to stop. And I should move this down. Okay, so here's two silting subcategories in type A3. So here the first one, I'm taking A3 with this zigzag orientation, and the tilting object I've taken is the standard tilting object. So it's a silting object, therefore it's silting, and it's just the projector. It's just the direction of the projector. This one here, I've actually just shift these two summers on, and I get something which is silting, but not tilting. In general, actually, in type A, it's the theorem of Kelvin-Bossick. Every silting object is obtained in such a way by taking a tilting object and shifting the, so you have a partial order among the summands. As long as you preserve that partial order when you shift, then you get a silting object. So this is how you get silting objects in type A. So these are two examples of silting. Maybe how much time? Then I think probably I leave it here and we start with mutation next time. So thank you.
Okay, we will thank the speaker from our side here. Any questions from the Zoom side? Can you hear me?
I can.
Well, here are the questions from the live audience. No? No questions from the live audience?
So if you have a part which isn't in the bigger length category, and how badly you can go wrong, you would both potentially to add the condition that the condition that you should get the central equation to the real condition, which would cut something else. But also to really specify the central charge. I mean, how bad can the reference group of the part actually be?
Well, if you've got one of these nice ones inside the growth manifold, then because the growth in the group of any half is isomorphic to the growth in the group of the right category, the growth in the group stays under control. But what can happen is, so for example, let me draw P1. So essentially, up to in P1 there are A1 cross A1 parts. There's so this is in, I say P1, but talking about the derived category. Parts of this. This is the quickest of bounded parts. So A1 cross A1. Chronic algebra, which looks something like this. So I have a P projected component, a regular component, a P injected component, and then I have coherent sheaves on P1, which is a tilted bit by moving the P injectors across. And then I have some funny hearts, which so I could tilt the P projectives across to the other side and get something looking like this. And then I can have something, say, I can move some of the regular modules across. And what you find is these are on D. And you get nice stability functions. You get there are hard and narrow symmetry filtrations here. These ones are not. That D, because the hard and narrow symmetry property becomes a real problem for these halves. So they're not defined here. For this one, so here the chambers associated with this guy is, it's H2. This is H2, but this, because all of these guys have to have the same phase in here. So most of the generic stability condition on here has every object semi-stable or can be mutated into or continuous. It's very close to one with everything semi-stable, but you're forced to have the same phases on everything here, please be semi-stable. And this gives quite a strong restriction. So this is really, I mean, it's on the boundary of these regions and it's kind of invisible. So you get something quite complicated. Well, it's not complicated, but you get sort of, so somehow the geometric one is, what's the best word? Maybe it's somehow like a limit point of the nicer algebraic ones. It's not visible.
Free back too, but you don't have to write down two generators given by something that looks like a simple object.
No, I mean your simple objects in this are very, you've got infinitely many ones sitting in here. And they don't generate.
Okay, great. Yeah, are there any questions? Any more questions, I guess? Okay, I cannot. No, okay. Yeah, let's thank the speaker then, and we will meet again. Are we still meeting in 1 minute?
Maybe 5 minutes.
Yeah.
Yes.
Okay, then yeah, let's thank the speaker again.